You think you know comets. Ice and rock, a cloud of gas, a tail streaming away from the sun. Every object in our sky follows that rule, every single one, until July 2025, when a telescope in Chile caught something moving wrong. 3I Atlas. The third visitor from beyond our solar system. And from the moment it arrived, it broke physics. Not broke, exactly, twisted. Because while every comet in history points its tail away from the sun, this thing aimed a jet straight at it. An anti-tail, a backward plume. Like watching smoke fall upward. Then, in September, without warning, the whole structure flipped. The anti-tail vanished. A normal tail appeared. The material that was streaming toward the sun reversed direction and started flowing away from it. No comet has ever done this, not in recorded history. The transformation happened between 3.8 and 1.8 astronomical units from the sun across a span of roughly 8 weeks. Scientists captured the entire sequence with the Nordic Optical Telescope in the Canary Islands. They watched the brightest pixel in the Coma shift from west to east. They measured the dust changing direction. They documented something that should not exist. The Asteroid Terrestrial Impact Last Alert System Survey Telescope at Rio Hurtado, Chile, code designation W68, picked up motion that didn't fit. By July 2nd, multiple observatories confirmed a diffuse coma with tail-like elongation measuring 3 arcseconds in angular length. The Minor Planet Center collected 122 observations from 31 observatories within 24 hours and assigned the designation 3I, third interstellar object confirmed. The first was 1I Oumuamua in October 2017. The second was 2I Borisov in August 2019. This one was moving at 221,000 kilometers per hour, 61 kilometers per second. Hyperbolic trajectory. Orbital eccentricity 6.1374. Not bound by the sun's gravity, came from outside. We'll leave outside. The Vera C. Rubin Observatory caught it during science validation runs from June 21st to July 3rd. NASA's Transiting Exoplanet Survey satellite had unknowingly recorded it back in May, when it was 6.4 astronomical units out and already active. That distance is critical. Water ice doesn't sublimate at that range. Something else was driving it. This script is researched and factual, using sources from the James Webb Space Telescope near-infrared spectrograph observations published in the Astrophysical Journal by Martin Cordner and colleagues on August 25, 2025, detailing carbon dioxide to water ratios of 7.6 to 1, and from David Jewett and Jane Liu's pre-Perihelion development paper submitted to ArcSiv on October 21, 2025, tracking the morphology shift from sunward fan to anti-solar tail across July through September. Now back to the information. The Hubble Space Telescope imaged 3I Atlas on July 21, 2025, at a distance of 277 million miles from Earth. The image showed something unprecedented, a teardrop-shaped cocoon of dust. But the elongation wasn't pointing away from the sun. It was pointing toward it. The glow extended twice as far sunward as it did perpendicular or opposite, a 2-to-1 ratio in projected space. When corrected for viewing angle, the actual three-dimensional elongation was 10 to 1, 10 times longer toward the sun than in any other direction. Avi Loeb and Eric Quito analyzed the brightness profiles in the Hubble data. They measured angles at 10 degrees toward the sun, 100 degrees perpendicular, and 190 degrees opposite. The sunward profile dominated. The scattered light formed a jet-like structure aiming directly at our star. Particles with sizes around half a micrometer, comparable to the wavelength of visible light, scatter sunlight efficiently and get blown back. That's why comets have tails, but 3I Atlas was doing the opposite. Material was collecting on the sunward side, extending farther toward the heat source than away from it. The structure resembled a plume or fan, brightest at the nucleus, and tapering as it stretched westward in telescope images. No conventional dust tail appeared behind the object. The glow in the anti-solar direction measured the same as the perpendicular direction. Symmetrical, except for that massive sunward extension. Perspective tricks where a wide dust tail appears to split, but that explanation collapsed under scrutiny. 3I Atlas was observed from multiple angles over weeks. The sunward feature remained consistent. David Jewett's team at UCLA proposed large dust grains. If the nucleus ejected millimeter-scale particles at low velocities, solar radiation pressure wouldn't move them quickly. They'd linger in front of the comet, creating a sunward fan before eventually being pushed back. The rotation of the nucleus could explain directional ejection. Material launched from the sunlit hemisphere would naturally start sunward before radiation pressure took over. Their model, published in September 2025 and expanded in October, laid out the physics. Carbon dioxide dominates the coma. The James Webb Space Telescope confirmed this on August 6, 2025, at a heliocentric distance of 3.32 astronomical units. Near-infrared spectroscopy, spanning 0.6 to 5.3 micrometers, revealed carbon dioxide emissions at 129 kilograms per second. Water emissions measured 6.6 kilograms per second, carbon monoxide at 14 kilograms per second, carbonyl sulfide at 0.43 kilograms per second. The carbon dioxide to water ratio was 7.6 to 1, among the highest ever recorded in any comet. 4.5 standard deviations above the trend for long-period and Jupiter family comets, excluding the outlier C 2016 R2. At 6.4 astronomical units, where TESS detected activity in May, the surface temperature allows carbon dioxide to turn directly from solid to gas. That gas erupts from the nucleus, carrying material with it, not just gas, solid fragments, ice chunks. The Keto-Loeb model calculates that as carbon dioxide sublimation accelerates on the sunlit side, it ejects water ice grains ranging from sub-micrometer to hundreds of micrometers in size. These grains scatter sunlight. The smaller ones evaporate quickly. But the larger ones, those around 100 micrometers, survive longer. And because they're launched predominantly from the sun-facing hemisphere where sublimation is strongest, they travel sunward before evaporating. The survival distance depends on the grain size and the illumination angle. Grains launched directly toward the sun have a maximum survival length. The model predicts that at 3.8 astronomical units, where Hubble captured the image, the largest water ice grains could survive 10 times farther toward the sun than perpendicular or away from it, 10 to 1, matching the observed elongation exactly. The emission showed a symmetric cloud declining with projected distance to the power of -3/2, corresponding to a density declining with three-dimensional radius to the power of -2.5. The cloud extended to at least 348,000 kilometers. No water gas emission was detected in S-X data, only an upper limit of 4.5 kilograms per second, but water ice signatures appeared in reflected light spectra, consistent with a mix of water and carbon dioxide ices combined with organics on the surface. The Swift Observatory detected hydroxyl and water vapor on July 30th and August 1st, 2025, through ultraviolet observations. Small icy grains released from the nucleus were heating up and vaporizing in sunlight, feeding the surrounding gas cloud. Then came the Keck telescope observations in August. The W.M. Keck Observatory on Mauna Kea detected hydrogen cyanide emissions. On September 7th, 2025, at 2.33 astronomical units from the Sun, the James Clerk Maxwell Telescope measured a hydrogen cyanide production rate of 1.5 times 10 to the 25th molecules per second. By September 14th, the rate had climbed to 4.5 times 10 to the 25th molecules per second, 2 kilograms per second. The cyanide coma on September 15th spanned 180,000 kilometers across and was asymmetric, elongated in the antisolar direction. On the same date, a visible dust tail appeared measuring 50 arc seconds across, corresponding to about 100,000 kilometers. The Very Large Telescope in Chile detected atomic nickel vapor emissions on August 23rd, 2025. Nickel without iron. Unusual. Nickel typically appears with iron when sublimated from comets. Pure nickel emission at temperatures too cold for direct nickel sublimation suggests nickel tetracarbonyl breaking down in ultraviolet light, releasing nickel and carbon monoxide. Nickel tetracarbonyl is highly volatile, rare in nature, unasto, commonly seen in industrial processes. Early estimates range from 10 to 20 kilometers, but astronomers knew those were too high. The dust loss rate suggested a nucleus likely under 1 kilometer in diameter, similar to 2I Borisov at roughly 0.5 kilometers. But other data complicated this. The Zwicky Transient Facility identified 3I Atlas in archival images dating back to May 15, 2025, at 6.1 astronomical units. The data showed a plateau period from May 15th to early June, where the reflecting area remained constant, suggesting the bare nucleus before substantial mass loss initiated. After June 1st, steady brightening began as the coma developed. If the plateau represented the actual nucleus, and the brightening came from added coma flux, then the nucleus diameter could be around 15 kilometers, 20 times larger than 2I Borisov. That would make the mass 8,000 times greater. Spherix flux measurements at 1 micrometer wavelength suggested an even larger diameter of 46 kilometers for a typical albedo of 4%. But if 99% of the brightness came from icy fragments rather than the solid nucleus, the diameter dropped to around 5 kilometers. Mass estimates based on these figures ranged from hundreds of billions of tons to 33 billion tons, depending on density assumptions. The carbon dioxide dominance indicated formation far from its parent star, beyond the carbon dioxide frost line where temperatures allowed carbon dioxide to condense into solid. This suggested 3I Atlas formed in the outer regions of a protoplanetary disk, possibly around a low metallicity star in the Milky Way's thick disk. If it originated from the thick disk, the comet could be 7 billion to 11 billion years old. Older than our solar system at 4.6 billion years. The heavy element abundance of its parent star would be at least 40% of the Sun's metallicity. Carbon-13 isotopes appeared in the James Webb data, though partial obscuration by dust made abundance measurements difficult. The high carbon dioxide content might result from exposure to higher levels of cosmic ray radiation during billions of years in interstellar space, or it might reflect the conditions near the carbon dioxide ice line in its birth disk. The Very Large Telescope, Nordic Optical Telescope, and Rosen Observatory measured light polarization from July through August 2025. 3I Atlas exhibited extreme negative polarization of negative 2.77% at small phase angles with a low inversion angle of 6.41 degrees, unprecedented for all known comets including 2I Borisov. The combination of low inversion angle and extreme negative polarization had never been observed in any object. The negative polarization meant a large percentage of reflected light had oscillations oriented along the Sun-Comet observer plane, similar to patterns seen in trans-Neptunian objects, suggesting a coma made of mixed icy and dark material. The polarimetric behavior might relate directly to the elongated 10:1 aspect ratio of scattered sunlight. Gemini South Telescope observations on August 27th showed the inner coma within 5 arcseconds of the nucleus appearing fan-shaped and slightly brighter on the sun-facing side, but the antisolar tail started growing. Hubble images from July 21st had shown a very faint antisolar tail pointing eastward, but the sunward fan dominated the optical appearance. Nordic Optical Telescope data showed the emergence of an obvious antisolar tail didn't occur until July 29th, fully 1 month after the first activity reports on July 2nd. By late August, Gemini South measured the antisolar tail at 30 arcseconds in angular length, roughly 56,000 kilometers. The tail was expected to become more obvious as the comet approached perihelion with changing viewing geometry and increasing activity. September brought the transformation. Images from the Nordic Optical Telescope tracking from early July through late September documented the complete morphology shift. The brightest pixel in the coma, marked with a red dot in processed images, showed the dust distribution changing. In July data, dust concentrated westward with no evident tail. In August, the distribution began shifting eastward as radiation pressure developed a tail structure. By September, the sunward fan had vanished and a clear antisolar tail dominated. The comet's appearance transitioned from a sun-facing dust fan to a structure with a conventional tail pointing away from the sun. David Jewett and Jane Liu published their analysis on October 21st, 2025. Fixed aperture photometry showed the comet's brightness following a power law function of heliocentric distance with an exponent of 3.8 across the 4.6 to 1.8 astronomical unit range. This indicated dust production rates varying in proportion to heliocentric distance to the power of negative 1.8. An inverse square variation is expected for strongly volatile materials, consistent with carbon dioxide as the primary activity driver. The Keto Loeb model explained the transition with temperature physics. As 3I Atlas approached the Sun, surface temperatures increased exponentially. The sublimation rate of carbon dioxide accelerated, causing a continuous increase in the production rate of ice fragments and a sharp decline in their residence time in the outflow. At 3 to 4 astronomical units, the total scattering cross-section of water ice grains peaked. Closer than that, the water ice grains evaporated too quickly. Scattering became dominated by longer-lived refractory dust particles and larger volatile grains, with survival times sufficient to form a conventional tail stretching away from the sun. The sunward extension disappeared because the ice grains that created it no longer survived long enough to travel sunward before evaporating. The transition was a natural consequence of changing temperature and sublimation physics, as distance to the sun decreased. Independent observations confirmed the tail growth. Keck telescope data showed reduction in the anti-tail and growth of an anti-solar tail in September. Gemini South observations from multiple dates tracked the same evolution. By late September, the coma morphology had completely inverted. Material that had been streaming toward the sun was now streaming away from it. The mass loss rate from 3I Atlas scaled roughly with the solar radiation flux impinging on its surface. From July through October, approximately 2 million tons of material left the nucleus. Given mass estimates ranging from hundreds of billions to 33 billion tons, this represented a loss of 0.00005% of total mass. A millimeter thick layer ablated from the surface over 10 years could sustain the observed carbon dioxide production. October 29, 2025. Perihelion. 3 Atlas reached its closest approach to the Sun at 1.36 astronomical units, 203 million kilometers, 126 million miles, between Earth's and Mars's orbits. The surface received at least 33 gigawatts of solar radiation. On October 21st, the comet entered solar conjunction, positioned directly behind the Sun from Earth's perspective, completely unobservable from terrestrial telescopes through early November. But spacecraft had other angles. The GOES-19 weather satellite observed during conjunction, ExoMars Trace Gas Orbiter with its color and stereo surface. Imaging system imaged the Coma on October 3, 2025, as the comet made closest approach to Mars at approximately 50 million kilometers. The orbiter used 5-second exposures to capture an object 50,000 times fainter than its usual targets. Mars orbiters provided sideways views unavailable from Earth. The HiRISE camera on Mars reconnaissance orbiter captured images on October 2nd at a distance of 29 million kilometers with a pixel resolution of 30 kilometers. Those images, according to sources, remained unreleased as of late October, possibly due to government considerations. ESA's Jupiter Icy Moons Explorer spacecraft, JUICE, en route to Jupiter, planned observations on November 4th, 2025, at a distance of 64 million kilometers. ESA's Hera spacecraft and NASA's Europa Clipper were expected to pass through the comet's tail between October 25th and November 6th to detect ions. NASA's Juno spacecraft orbiting Jupiter would observe 3I Atlas on March 16, 2026, at 54 million kilometers distance using ultraviolet, infrared, and radio sensors. The comet's trajectory would bring it within 0.65 astronomical units of Venus on November 3, 2025. Closest approach to Earth would occur December 19, 2025, at 1.8 astronomical units, 269 million kilometers, 167 million miles. Never closer. No collision threat. After Earth passage, the comet would swing by Jupiter on March 16, 2026, at 0.36 astronomical units, 54 million kilometers, then exit the solar system permanently, continuing its journey through the Milky Way. 3. Atlas's orbital path aligned within 5 degrees of the ecliptic plane, the flat disk where planets orbit the Sun. For a random interstellar object entering from any direction, the probability of aligning this closely is 1 in 500. Oumuamua showed similar alignment. 2. Borisov did not. The high velocity, 68 kilometers per second at perihelion relative to the Sun, indicated billions of years accelerating through gravitational encounters with stars and molecular clouds. Tracing the trajectory backward placed the origin somewhere in the galactic thick disk, but the countless gravitational nudges over millions or billions of years made pinpointing the original star system impossible. The interstellar origin was certain, the starting point was not. Avi Loeb assigned 3I Atlas a ranking on his scale measuring the likelihood an interstellar object has technological rather than natural origin. 0 represents definitely natural. 10 represents definitely technological. He initially ranked it at 4 based on 8 anomalies. The ecliptic alignment, the sunward jet, unlike familiar comets. The mass roughly 1 million times greater than Oumuamua and 1,000 times greater than Borisov, while moving faster than both. Arrival timing allowing close passes to Mars, Venus, and Jupiter while being unobservable from Earth at perihelion. Extreme negative polarization unprecedented for all known comets. Direction of arrival, within 9 degrees of the WOW signal source from 1977. Possible nucleus diameter, up to 46 kilometers. The nickel emissions without iron. After the anti-tail to tail transition, he raised the ranking to 6, then suggested it might reach 8, depending on post-perihelion observations. He noted the transition could represent either natural comet physics or a braking thrust maneuver. Post-perihelion observations on December 19th at closest Earth approach would test the hypothesis. If the comet glowed naturally from solar heating and displayed all expected cometary features, he would reduce the ranking to 2. But the large mass and ecliptic alignment would remain unexplained. Jason Wright at Penn State pointed out that anti-tails, while rare, have been observed before. Comet Kohoutek in 1974. Comet C, 2014, UN 271. Bernardinelli Bernstein showed similar sunward enhancement from slow ejection of large dust particles from the sunlit hemisphere. Michael Bush explained that rotating comet nuclei eject material from spots that come off with velocities, placing ejecta both in front of and behind the nucleus regardless of launch side. Small dust and gas get pushed by radiation pressure and solar wind. Larger ejecta spread along the orbit in both directions, eventually forming meteoroid streams. Casey Lisa, lead author of a paper providing nucleus size estimates, noted that the 46-kilometer figure represented a reference point for a coma-free object and explicitly cited a smaller upper limit around 5 kilometers. The anti-tail of 3 Atlas, while unusual, fit within known comet physics for distant active bodies, ejecting large dust slowly. 6.1 standard deviations above the trend for solar system comets at that distance. Only C 2016 R2, a hypervolatile rich outlier, showed comparable deviation. The ratio suggested intrinsic carbon dioxide richness, possibly from formation near the carbon dioxide ice line or from cosmic ray irradiation during interstellar travel, suppressing water content. Alternatively, inhibited heat penetration into the nucleus could suppress water sublimation relative to carbon dioxide and carbon monoxide. The JWST observations estimated active sublimating surface areas of 3.1 square kilometers for carbon dioxide and 2.2 square kilometers for water, assuming a non-rotating spherical nucleus with infrared emissivity 0.95 and albedo 5%. The nucleus radius upper limit was 2.8 kilometers based on the data, but separating nucleus light from coma light remained challenging. This analysis comes from multiple peer-reviewed sources, including the ArcSavism preprint server hosting papers by Jewett, Liu, Keto, and Loeb, submitted October 2025, and from NASA Hubble, Space Telescope observations published in the Astrophysical Journal, Letters on August 7, 2025, showing the teardrop coma at 277 million miles distance. These sources provide the specific measurements, dates, wavelengths, and production rates that anchor every claim back to the sequence. Photometric observations in July showed brightness variations decreasing from 0.3 to 0.2 magnitudes throughout the month, likely indicating the nucleus becoming more obscured as activity increased. Analysis of coma shape in Hubble images suggested the rotational North Pole pointed toward either right ascension 154 degrees, declination plus 25 degrees, or right ascension 334 degrees, declination minus 25 degrees. The coma appeared slightly elliptical, spanning up to 26,400 by 24,700 kilometers in diameter, about twice Earth's diameter. High-resolution images from the Gran Telescopio Canarias showed the coma growing from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. Pre-discovery test observations showed the comet active in May at 6.4 astronomical units when water ice doesn't sublimate efficiently, confirming that supervolatiles like carbon dioxide were driving early activity. Spectroscopic and imaging observations indicated the coma contained relatively large dust grains several micrometers in radius. Within the coma, small dust grains with 1 micrometer radii ejected at fast speeds of 22 meters per second. Large dust grains with 100 micrometer radii ejected at slower speeds of about 2 meters per second. The reddish color of 3I Atlas resembled D-type asteroids, solar system comets, and 2I Borisov, likely caused by irradiated organic compounds such as tholins. The color evolved through July, becoming redder as surface or coma composition changed with increasing activity. The delayed emergence of the antisolar tail carried significance. Jewett and Liu attributed it to the large size and slow ejection of optically dominant dust particles and their sluggish response to solar radiation pressure. Effective radius 100 micrometers, ejection speed 5 meters per second. These particles took time to accelerate under radiation pressure. The lag between initial activity on July 2nd and obvious tail formation on July 29th matched predictions for large, slowly ejected grains. As 3, I-Atlas moved from 4.6 astronomical units in early July to 1.8 astronomical units by late September. The tail length increased from undetectable to tens of thousands of kilometers. The viewing geometry changed as Earth's position relative to the comet shifted, making the tail more visible, but the fundamental driver was increasing solar flux. Closer to the Sun meant higher surface temperatures, faster sublimation, more gas production, more dust lofting, stronger radiation pressure, longer tails. The physics scaled with distance to the power of roughly -2, the signature of volatile-driven activity. September 15th, 2025. The antisolar tail measured 100,000 kilometers. The cyanide coma spanned 180,000 kilometers, asymmetric and elongated away from the Sun. The hydrogen cyanide production rate hit 4.5 times 10 to the 25th molecules per second. Nickel vapor emissions continued. Carbon dioxide remained the dominant species, accounting for 87% of mass loss, with carbon monoxide at 9% and water at 4% based on JWST data from August. As the comet approached perihelion through October, production rates increased exponentially. Surface temperatures climbed, sublimation accelerated. The question was whether the nucleus would fragment under thermal stress like 2I Borisov, which broke apart during its perihelion passage. Through August and September, no outbursts were detected. Brightness and activity remained steady. No sudden brightening, no fragmentation signatures. The nucleus held together. This creates a self-limiting process. The sublimating carbon dioxide cools the surface through latent heat absorption. The cooling prevents runaway heating that could lead to explosive outgassing or fragmentation. As long as carbon dioxide dominates, the thermal balance stays controlled. Only when water sublimation becomes significant, typically inside 1.5 astronomical units, does the heating potentially become unstable. 3. Atlas at perihelion sat at 1.36 astronomical units, right at the threshold. Post-perihelion observations would reveal whether water sublimation ramped up and whether the nucleus survived intact or began breaking apart. The International Asteroid Warning Network announced a training exercise to monitor 3I Atlas from November 27th through January 2026. The exercise aimed to refine orbital calculations and tracking procedures for fast-moving interstellar objects. The network emphasized the unique challenges posed by 3I Atlas: hyperbolic trajectory traveling over 210,000 kilometers per hour, rapid changes in position, limited observation windows. The exercise involved telescopes worldwide coordinating to maintain continuous tracking. No collision risk existed, but the opportunity to practice protocols on a real interstellar visitor passing through the inner solar system was unprecedented. The data gathered would improve preparedness for future objects that might pose actual threats. The age estimates ranged from 3 to 14 billion years, with some models suggesting as old as 11 billion years. If 3I Atlas formed 7 to 11 billion years ago, it predated the solar system and originated during an earlier epoch of star formation in the galaxy. The chemical composition would reflect conditions in protoplanetary disks from that era, potentially differing from solar system formation environments. The high carbon dioxide content might be characteristic of planet-forming regions around older, lower metallicity stars. Or it might result from processes during the billions of years spent in interstellar space, subjected to cosmic ray bombardment and ultraviolet radiation that could alter surface chemistry. Distinguishing between primordial composition and space weathering effects requires more data than a brief passage through the inner solar system provides. In orbital mechanics, the Oberth effect describes how thrust applied at high velocity, particularly near perihelion, where an object moves fastest, produces the maximum change in kinetic energy. A spacecraft using chemical or ion propulsion could exploit this by firing engines at perihelion to alter trajectory more efficiently than firing at aphelion. Loeb noted that if 3I Atlas possessed propulsion capability, perihelion on October 29th would be the optimal moment to execute a maneuver, behind the Sun from Earth's view, unobservable, maximum velocity, gravitational assist available. Any trajectory change initiated there would manifest most effectively. The timing of the solar conjunction aligned perfectly with when an engineered object would want to maneuver undetected, but the timing also aligned with natural orbital mechanics. Every interstellar object on a hyperbolic trajectory reaches perihelion at some point. That it occurred during conjunction was a consequence of the orbital geometry, not necessarily evidence of design. The probability calculations for the ecliptic alignment at 1 in 500 carried more weight as an anomaly than the conjunction timing. If 3I Atlas behaved as a natural comet enriched in carbon dioxide, water sublimation would increase dramatically inside 1.5 astronomical units. The tail would grow larger, dust production would spike, the coma would expand. Gas production rates would follow exponential curves matching surface temperature increases. Spectroscopic observations in December would show whether water emission dominated or whether carbon dioxide remained primary. If water dominated, the object followed typical comet evolution. If carbon dioxide still dominated at 1 astronomical unit or less, the thermal properties of the nucleus were unusual, possibly indicating high thermal conductivity or low porosity preventing heat penetration. If the object fragmented, pieces would separate along the orbital path, detectable through multiple brightness peaks in photometry. If the object dimmed unexpectedly or showed non-gravitational acceleration inconsistent with outgassing, alternative explanations would gain traction. The December 19th closest approach to Earth at 1.8 astronomical units, 269 million kilometers, provided the critical observation window. Apparent magnitude predictions placed the comet around magnitude 12 to 13, too faint for naked eye but visible in 8-inch or larger telescopes. Multiple ground-based facilities planned observations. Space telescopes including Hubble, James Webb, and Swift would track it. The viewing geometry would be favorable. Earth's position relative to the comet's orbit would allow side view perspectives of the coma and tail. Measurements would include spectroscopy across ultraviolet, visible, and infrared wavelengths to determine composition changes, photometry to track brightness variations and detect outbursts or fragmentation, imaging to measure coma size and tail length and morphology, and polarimetry to characterize dust properties and compare with earlier measurements. The data collected in December would either confirm natural comet behavior or reveal continued anomalies. In solar system comets, nickel and iron sublime together because they occur together in silicate and metal grains. Seeing nickel alone at temperatures too cold for direct sublimation suggests a carrier molecule. Nickel tetracarbonyl, chemical formula NiCO.4, is volatile enough to sublime at low temperatures and photolyzes in ultraviolet light to release nickel atoms. But nickel tetracarbonyl is rare in nature. It forms in industrial processes under specific conditions. Finding it in a comet requires explaining how it formed in a protoplanetary disk. Possible mechanisms include carbon monoxide-rich environments reacting with nickel-bearing grains under pressure and moderate temperatures. Some carbon-rich stellar environments could produce it. But the abundance needed to explain the observed nickel emission would require formation conditions, unlike those typical of solar system comets. Alternative explanations invoke subsurface chemistry or complex organic molecules carrying nickel. The data remained ambiguous. The trajectory after Jupiter flyby on March 16, 2026, will carry 3I Atlas out of the solar system at escape velocity. The object will climb through the Kuiper Belt, cross the heliopause where the solar wind meets interstellar medium, and resume wandering the galaxy. Velocity. Relative to the local standard of rest, the average motion of stars in the solar neighborhood will be tens of kilometers per second. Over the next million years, it will travel roughly 30 light years. Over a billion years, it will traverse thousands of light years, encountering other stars, drifting through molecular clouds, subjected to continuous cosmic ray bombardment and occasional gravitational perturbations. If it survives intact, it might eventually enter another star system. If it originated from a thick disk star 7 to 11 billion years old, it has already spent billions of years in interstellar space. Its surface chemistry, isotopic ratios, and internal structure carry records of those epochs. A flying archive, a messenger from the deep past of the galaxy. But the anti-tail-to-tail transition stands as the central mystery. The physical explanation from Kido and Loeb fits the data. Carbon dioxide sublimation ejects water ice grains. Larger grains survive longer. Enhanced sublimation on the sunlit side creates directional asymmetry. At greater distances, ice grains dominate scattering and extend sunward before evaporating. At closer distances, ice grains evaporate too quickly and refractory dust dominates, forming a conventional antisolar tail. The transition occurs at 3 to 4 astronomical units, where the sublimation timescale equals the dynamic timescale for grains to separate from the nucleus. The model predicts the observed 10 to 1 elongation ratio in July, the gradual reduction of the sunward feature through August, and the dominance of the antisolar tail by September. The mass loss rate, scaling with solar flux, matches observations. The predicted peak in scattering cross-section at 3 to 4 astronomical units matches the timeline of the transition. Large dust grains with radii around 100 micrometers, ejected at speeds around 5 meters per second, respond slugly to radiation pressure. They accumulate sunward initially before slowly accelerating antisolar. The delayed tail emergence from July 2nd to July 29th matches the timescale for 100 micrometer grains to accelerate under radiation pressure. As the comet moves closer, dust production increases, more grains enter the coma, radiation pressure builds, the tail develops. The sunward fan represents dust lingering before radiation pressure becomes effective. The morphology change reflects increasing dust production and stronger radiation forces as heliocentric distance decreases. Both models invoke natural physics. Both match the timeline. Both predict the observations. The brightness curve followed a smooth power law. No outbursts detected, no sudden changes. The transition from anti-tail to tail occurred gradually over weeks without disruption. The activity scaled cleanly with heliocentric distance. The production rates increased exponentially as expected from temperature-driven sublimation. The nucleus remained intact. The coma remained symmetric. For a comet potentially billions of years old, subjected to interstellar cosmic rays, entering the solar system for possibly the first time in its existence, the behavior was remarkably controlled. That control might indicate a volatile-rich composition dominated by carbon dioxide providing stable sublimation, or it might indicate something else. Negative 2.77% with inversion angle 6.41 degrees. No other comet shows this combination. Trans-Neptunian objects show similar polarization, but they're not actively sublimating. The polarization depends on particle size distribution, composition, and geometric arrangement of scattering material. If the coma contains a specific mix of icy and dark particles in a unique size distribution, it could produce the observed polarization. If the elongated 10-to-1 coma geometry affects polarization measurements by creating preferential scattering directions, that could contribute. But calculating the exact polarization from first principles requires detailed modeling of particle properties and distribution. The measurement stands as an outlier until another comet with similar characteristics appears for comparison, or until 3I Atlas produces different polarization in December observations under changed geometry and activity levels. NASA's Planetary Defense Protocol activation in response to 3I Atlas involved the International Asteroid Alert Network, coordinating data sharing and trajectory modeling. The protocol exists to assess potential impact risks from near-Earth objects. 3I Atlas never posed collision threat. Closest approach 1.8 astronomical units well beyond Earth orbit. But the unusual behavior, erratic brightness changes reported in some early observations, and uncertain trajectory prompted precautionary measures. The network mobilized to ensure accurate orbit determination and rule out non-gravitational forces that could alter the path. The protocol also served as a training exercise, testing communication channels and response procedures on a fast-moving object with limited observation windows. The results would inform future responses to actual threats. That resolution is sufficient to resolve the inner coma structure and test whether the glow is optically thin, as the Keto lobe model predicts. If the coma is transparent, the brightest pixel in the image should show the nucleus position. The total luminosity from that pixel would provide a strict upper limit on nucleus brightness and therefore size, 2 orders of magnitude better than Hubble data. If the coma is optically thick, the central brightness would be dominated by scattering from dense material obscuring the nucleus. The distinction would constrain nucleus diameter to either under 5 kilometers for transparent coma or potentially larger for opaque coma. The images exist. Their release depends on NASA and the Mars Reconnaissance Orbiter team. The Keto lobe papers, submitted to ARCIF as preprints, underwent scrutiny. Other astronomers noted that anti-tails from large particles are not unprecedented despite claims in the papers. The Farnham paper on Comet Bernardinelli-Bernstein from 2021 explicitly described sunward enhancement from slow ejection of large dust particles. The mechanism was known. What made 3I Atlas notable was the extreme degree of elongation, the 10-to-1 aspect ratio, and the dramatic transformation over 8 weeks. But calling it unprecedented overstated the case. The theoretical model itself faced questions about assumptions. The model assumes spherical ice grains with specific size distributions and sublimation rates. Real grains have irregular shapes affecting surface area and evaporation. The model assumes uniform illumination and ejection only from the sunlit hemisphere. Real nuclei rotate and have irregular shapes, creating complex ejection patterns. The model predicts peak scattering at 3 to 4 astronomical units. Observations confirm the transition occurred in that range. But whether the peak resulted from ice grain evaporation or from changing dust production rates with distance is not conclusively determined by fitting one parameter to one dataset. If 3I Atlas at 1 to 2 astronomical units still shows unusual features, unusual polarization, unusual tail morphology, unusual spectroscopic signatures, then the anomalies persist under different conditions and demand deeper explanation. If it looks like a normal carbon dioxide-rich comet with predictable water sublimation ramping up, with conventional tail and coma, with polarization matching other active comets, then the anti-tail episode was an artifact of distance, viewing geometry and composition. The object is natural, just unusual in its carbon dioxide enrichment and possibly in its age and origin from a low metallicity stellar environment. Natural but rare, a billion-year-old time capsule from an ancient star system. Following Oumuamua, which showed no activity and was never definitively classified as comet or asteroid, despite likely being ice-rich with a reflective organic crust. Following 2I Borisov, which displayed normal comet behavior almost identical to solar system comets, suggesting commonality of planet formation processes across the galaxy. 3I Atlas fits neither pattern, more massive than Oumuamua by 1,000,000 times. More active than Borisov at comparable distances, chemically distinct from both, morphologically unusual with the anti-tail, polarimetrically unprecedented, compositionally carbon dioxide dominated unlike any solar system comet, except one outlier, age potentially double the solar system's age. Origin from the galactic thick disk, rather than the thin disk where most stars and the sun reside. Every measurement adds detail, but the overall picture stays fragmented. That transformation, documented across 4 months by multiple independent observatories using different instruments and techniques, remains the clearest fact. July showed a sunward feature. September showed an anti-solar feature. The transition happened as heliocentric distance decreased from 3.8 to 1.8 astronomical units. Production rates increased, sublimation accelerated, grain sizes shifted, radiation pressure strengthened. Material that was extending toward the sun started extending away from it. The geometry inverted, the flow reversed. The object that arrived pointing wrong flipped to pointing right. And that flip, whether from evaporating ice or accelerating dust or something not yet considered, whether natural physics or something else entirely, tells us that interstellar space still holds surprises. That comets from other stars don't always behave like the comets we grew up with. That the galaxy is older and stranger and more varied than our one system prepared us for. The project includes telescope networks, infrared sensors, and tracking systems aimed at gathering high-quality data on unusual objects in near-Earth space and the solar system. 3, iAtlas became a target for Galileo instruments, with data collection planned during its December passage. The project represents a shift toward empirical investigation of low-probability, high-impact hypotheses. Whether 3 iAtlas proves natural or remains ambiguous, the methodology of systematic observation and data-driven analysis applied to interstellar visitors establishes a framework for studying future objects. The statistical expectation is that the Vera Rubin Observatory, once fully operational, will detect several interstellar objects per year. Each one provides a data point on the distribution of sizes, compositions, and trajectories in the local interstellar medium. Building a population sample allows distinguishing between typical and outlier objects. The brightness will be tracked. The trajectory will be refined with post-perihelion data, testing for non-gravitational accelerations. The nucleus size will be better constrained. The production rates of water, carbon dioxide, carbon monoxide, cyanide, nickel, and other species will be quantified. The polarization will be remeasured under different phase angles and activity conditions. The rotation period might be determined from brightness variations. Fragmentation or survival intact will be established. By January 2026, the observational campaign will be complete. The data will be published, the models will be tested, the rankings and probabilities will be updated, and the object itself will be past Jupiter, climbing out of the inner solar system, leaving the warmth and light behind, returning to the cold and dark of interstellar space. But the measurement that changes everything will be simpler. Does the object glow in December where no sunlight illuminates it? The load prediction states that if 3 iAtlas shows anomalous luminosity on its post-solar side, the side facing away from the sun that should be dark and cold, then solar heating cannot explain the glow. Technological heat sources, internal power, active thermal management, something beyond passive comet physics would be required. If the post-solar side is dark as expected, if all luminosity comes from the sun-facing side as predicted by thermal models, then the object is natural. The test is binary, glow or no glow, light or dark, natural or not. 30 kilometers per pixel, resolution sufficient to see the Coma structure, images stored, data archived, waiting for release, possibly delayed by government shutdown, possibly held for analysis, possibly classified for reasons unknown, possibly routine processing backlog. The images exist. They contain information about the nucleus size and Coma opacity. Whether that information supports natural comet models or contradicts them depends on what the pixels show. The answer is already captured. We just can't see it yet. The Nordic Optical Telescope images from July through September told a story. The brightest pixel migrated. The dust redistributed. The morphology transformed. The sunward glow faded. The anti-solar tail emerged. Day by day, observation by observation, the structure inverted. No other comet has been documented undergoing this specific transition in real time. No other interstellar visitor has been tracked with this intensity across this many facilities. The dataset for 3 iAtlas exceeds that for Oumuamua and Borisov combined. More telescopes, more wavelengths. More time, better instruments, higher resolution, fuller coverage. And still the interpretation splits. Natural comet with unusual composition and viewing geometry, or engineered object masquerading as natural through sophisticated mimicry of comet physics. The data supports both. The absence of definitive evidence for technology doesn't prove its absence. The presence of explanations based on natural physics doesn't prove they're correct. The object fits the evidence we have, but the evidence we have isn't complete. It will come from a mass grave of expectations, not literal graves, conceptual ones, the graveyard of predictions that didn't pan out. If post-perihelion observations in December show all features consistent with natural comet behavior, the technological hypothesis gets buried alongside countless other incorrect interpretations of astronomical phenomena. If post-perihelion observations show persistent anomalies, unexplained luminosity, trajectory changes without outgassing to explain them, signals or emissions inconsistent with passive thermal physics, then the natural comet hypothesis gets buried and the investigation escalates. One set of predictions will die, the other will survive. The data will decide. Not opinion, not probability arguments, not prior beliefs about what should or shouldn't exist in interstellar space. Just measurements, just photons counted, just spectra analyzed, just trajectories calculated. The anti-tail turned into a tail. 3-eye Atlas arrived pointing at the sun and left pointing away from it. The transformation happened between 3.8 and 1.8 astronomical units over 8 weeks, from July to September 2025. Documented by David Jewett and Jane Liu using the Nordic Optical Telescope in the Canary Islands, Spain, and confirmed by independent observations from Keck Observatory in Hawaii and Gemini South Observatory in Chile, showing reduction in anti-tail and growth of conventional tail away from the sun. The physics behind the transformation can be explained by temperature-dependent sublimation rates of carbon dioxide-ejected water ice fragments, whose survival distance decreases as heliocentric distance decreases, causing the dominant scattering signature to shift from long-lived sunward ice grains. At 3 to 4 astronomical units to conventional antisolar dust tail at closer distances. Or it can be explained by a gradual acceleration of large dust grains under increasing radiation pressure as dust production rates scale with heliocentric distance. Both models fit, both are natural. Both make predictions testable in December. We're tracking an object through its entire inner solar system passage with full observational coverage pre-perihelion, at perihelion via spacecraft, and post-perihelion from Earth. We're measuring composition with the most advanced spectrographs ever deployed. We're imaging with Hubble and James Webb and Mars orbiters. We're modeling with physics refined over decades of comet observations. We're comparing with 2 previous interstellar visitors and thousands of solar system comets. We have context, we have baselines, we have predictions. December 19th, 2025. At 269 million kilometers distance, we'll test those predictions. The object will be there. The telescopes will be watching. The data will flow. The analysis will proceed. The answer will emerge. Not immediately, not simply, but eventually. Definitively, one way or the other, natural or not. Comet or something pretending to be one well enough to pass every test we throw at it until it doesn't.